Hello, my name is Roxen Ajiman and I am from the University of Klagenfurt in Austria. Today I shall be presenting the details of our position paper which we have titled Resource Efficient Pervasive Smart Camera Networks. This paper is co-authored by Professor Bernardina, also from the University of Klagenfurt. This would be the outline of my presentation today. Let's begin with the introduction. Today, smart cameras are everywhere. They are in our homes, in our offices, on our highways, at the train stations, at the airport, at the parks, and in other public spaces, to name but a few. Smart cameras are mostly used to provide security through surveillance, and this is done through applications such as motion detection, object tracking, and object re-identification, to name but a few. Modern surveillance systems have evolved from the use of single cameras to the use of a network of cameras. One of the advantages this provides is the convenience of extensive coverage. The pervasive adoption of cameras is made possible by some enabling technological trends, and we shall quickly review these on the next slide. First of all, modern cameras can now sense more than one sensor modality. Early versions of smart cameras could sense and generate RGB image data only. However, modern smart cameras can perform image depth sensing, infrared image sensing, as well as acoustic information sensing. Most smart cameras have fixed orientations. However, in recent times, it is possible to control the orientation of surveillance cameras using panning and tilting, thus transforming camera networks into a sensor actuator network. Secondly, modern cameras come with advanced CPUs and expanded memory for onboard data processing. Last but not the least, modern cameras have networking or communication capabilities. This allows visual data to be transmitted across multiple cameras or to a dedicated central location. These enabling technologies have become the foundation of surveillance applications in multi-camera networks. Existing surveillance applications typically employ a centralized architecture. To give us an idea of the centralized architecture I am talking about, let us take a quick look at this person monitoring example on the next slide. Let us consider this geographical space. It's the campus of a university. For monitoring purposes, let's assume we have these number of cameras distributed across different geographical locations. Let's assume a person, X, is going to move all the way from building S to building V. In existing monitoring applications, as the entity transitions different camera views, videos or images are collected from the person by the different cameras and transmitted to a central location. Over time, a database is built on all the people that have transitioned or moved through the views of all the cameras. A curious question is, why the architecture? Surveillance applications such as object detection, object tracking, and person re-identification are primarily computer vision based artificial intelligence tasks. Therefore, they have very high computational requirements, and they require very large memory and have very high energy consumption footprints. Now, because smart cameras are primarily sensor nodes and have resource constraints, it makes onboard processing of complex surveillance applications very challenging. Let us consider some of the ways researchers over the years have tried to achieve resource efficiency in smart cameras. First, let's look at duty cycling. Duty cycling refers to temporarily powering down hardware components when they are not in use. Some duty cycling methods include sleep modes and dynamic power management. In the end, the goal of duty cycling is to promote efficient power utilization. Let's now consider data reduction. As the name implies, data reduction refers to reducing the quantum or dimensionality of data required for processing. Data reduction and data compression techniques promote computation and network efficiency. Let's now consider in-network processing. In-network processing fosters task decentralization. That is, tasks are processed locally on camera nodes and only abstracted data are transmitted to other nodes in the network. In-network processing, however, reduces data communication at the cost of local data processing. The challenges usually associated with in-network processing includes 1. How to distribute the processing efficiently, and 2. What type of abstracted data should be transmitted. Despite the seeming limitation, in-network processing promotes efficient memory and network utilization. Let's now consider hardware mapping. Hardware mapping is the development of application-specific hardware components for efficiently mapping software functions to dedicated hardware. Examples of such hardware platforms include application-specific integrated circuits, FPGA, that is field programmable gate arrays, and graphical processing units, commonly referred to as GPU. Hardware mapping results in significant performance improvements and efficient resource utilization. However, the development effort is typically greater than on traditional general purpose processors. Last but not the least, let's look at the development of resource-aware algorithms. Machine learning algorithms, in particular deep learning, are nowadays used in numerous camera network applications. Although these applications are superior to their native counterparts, they typically require resources beyond what most embedded devices can support. Two strategies for promoting resource efficiency are 1. Model size reduction, and 2. Arithmetic precision reduction. In model size reduction, the objective is to reduce the number of model parameters, thus conserving memory utilization. In arithmetic precision reduction, however, the objective is to reduce model complexity by reducing the precision of floating point numbers. For example, in extreme cases, floating point numbers can be reduced to binary representations to take advantage of hardware-friendly bit operations. So far, we've been talking hypothetically about smart cameras and how their resource limitations affect the practical deployment of surveillance applications. Let's now delve into specifics by considering person re-identification as a surveillance application example of smart camera networks. Person re-identification is a research domain of content-based image retrieval, and it is defined simply as searching a person of interest from a large database using a query, also referred to as a probe. Previously, when we were considering person monitoring example, we looked at how the database of persons is generated. The probes are largely in the form of image or image sequence, but in recent times there's been a growing interest in using textual descriptions as the probe. A key question is, why are person re-identification applications commonly implemented using the centralized camera network architecture? To answer this, let us do a quick survey of existing natural language-based person re-identification algorithms. Table 1 summarizes the minimum resource requirements of some of the existing state-of-the-art natural language-based person re-identification methods. Specifically, Table 1 presents the memory and computational requirements of the visual components of existing re-ID methods, person re-identification methods. As shown, the methods use backbone convolutional neural networks that are designed for general purpose image classification tasks. Indeed, these two metrics do not represent the overall resource requirement of re-identification algorithms, but it rather seeks to present an estimation of the barest minimum resources required to perform person re-identification. Because these backbone CNNs require much memory and computation beyond what camera nodes can support, existing person re-identification applications require that images are collected from multiple cameras and transmitted across a communication network to a high-performance central processing entity. In other words, existing re-identification methods are too computationally expensive to be processed locally on camera nodes. To solve the problem of decentralizing person re-identification in camera networks, we propose a two-part framework, or a blueprint as it can also be referred to as. Specifically, the concept of the framework aims at performing person re-identification locally on smart cameras and avoiding sending raw data to high-performance computing entities or cloud servers. This proposed framework is in two stages. Stage 1 involves designing and optimizing the size of re-identification algorithms to meet the resource specifications of camera nodes. In stage 2, it involves implementing the re-identification framework on camera nodes such that cameras within a network can collaborate with each other to retrieve a person of interest globally. In stage 1, different from existing state-of-the-art works, we propose a re-identification algorithm based on human parsing, and we reduce the memory and computational footprints using lossy compression algorithms. We have not shown any results in this paper because of ongoing work. However, preliminary results on exploiting lossy compression algorithms for developing memory-efficient re-identification models prove promising, and this is the basis for our future work. Algorithm 1 is our proposed algorithm for performing person re-identification. It receives as input a local gallery, person retrieval score threshold, and also the textual description of the entity we are looking for. And as an output, it returns a gallery, a subset of the gallery, which can contain one person or a group of entities that meet the description criteria. And so for each entity, for each gallery element, it performs human parsing, and it estimates the retrieval score. And if the retrieval score is greater than a threshold, then it returns that particular image as well as its retrieval score. In stage 2, we focus on deploying the re-identification algorithm on camera nodes instead of using a dedicated high computing server. A naive approach is to execute an instance of the re-identification algorithm on each camera node, and all the cameras with a re-identification accuracy beyond a threshold can stream video to the monitoring station. Now, the downside to this naive approach is that no camera knows what the other is seeing or sensing. Therefore, if a false positive identification is made, multiple cameras can stream video to the monitoring station. To overcome this limitation, we propose a collaborative approach. In the collaborative approach, each camera node keeps an up-to-date record of all the active cameras in the network. And we summarize this in algorithm 2. It's supposed to be a long one, but because of space, it's been broken into 2. So as I mentioned, to overcome this limitation, we propose a collaborative approach. And in the collaborative approach, each camera node keeps an up-to-date record of all the active cameras in the network. Therefore, a search query from the monitoring station will require that all cameras communicate with each other to compare their retrieval confidence scores. Now, the camera with the highest retrieval score assumes or temporarily assumes the role of the master camera and streams the video of the person of interest to the monitoring station. It does this by locking a tracking mechanism on the person of interest. Now, when the person of interest leaves the field of view of the temporal master camera, the said camera gives up the master status to other cameras to find the person of interest. A further improvement to the collaborative approach is exploiting neighborhood or topographical information of other cameras in the network. By knowing the location of all cameras and predicting which camera's field of view a person of interest is likely to transition into, it will be possible to limit the number of cameras performing or participating in the person's search, thus ultimately conserving computational and network resources. Finally, the conclusion of my presentation. This position paper presented a framework for practically decentralizing person re-identification in smart camera networks. Specifically, the concept of the framework aims to perform person re-identification locally on smart cameras and avoid sending raw data to a high-performance computing entity or cloud service. This proposed framework is in 2 stages. 1, optimizing the size of re-identification algorithms to meet the resource specification of camera nodes. And 2, implementing the re-identification framework on camera nodes in a collaborative manner such that cameras within a network can collaborate with each other to retrieve a person of interest globally. As I mentioned, we do not show any results in this paper because of ongoing work. However, preliminary results on exploiting lossy compression algorithms for developing memory efficient re-identification algorithms prove promising, and this is the base for our future work. This is the end of my presentation. If there are any questions, comments, recommendations, I'm very happy to take them. Thank you.